There's an object in our solar system right now that breaks every single rule we thought we understood about comets, and the more scientists study it, the stranger it gets. I'm talking about 3I Atlas, the third interstellar visitor we've ever detected. And here's what nobody's telling you. This thing is so bizarre, so completely different from anything we've ever seen, that some researchers are quietly asking questions they never thought they'd have to ask. Questions about where it really came from. Questions about what it actually is. Because when one thing about an object is weird, that's interesting. When two things are weird, that's a coincidence. But when literally everything about it violates what we know about natural objects in space, that's when scientists start looking at each other across the lab and wondering if they're missing something big. Stay with me, because what I'm about to show you isn't speculation. This is real data from the James Webb Space Telescope, the Hubble Space Telescope, and dozens of other instruments that have been watching this object for months. And the picture they're painting is one that challenges everything we thought we knew about comets, about interstellar objects, and maybe even about what's possible out there in the galaxy. By the end of this video, you're going to understand why 3I Atlas isn't just another space rock. You're going to see the evidence that's making astronomers lose sleep, and you're going to learn about a connection to something that happened almost 50 years ago that makes this whole story even more unbelievable. Let's start with the basics, because understanding just how wrong everything is about this object requires knowing what normal looks like. On July 1, 2025, the Atlas Survey Telescope in Chile picked up a faint dot moving across the sky. At first, nobody thought much of it. Telescopes spot thousands of objects every year. Most of them are asteroids from our own solar system, following predictable orbits that we can calculate centuries into the future. But as astronomers collected more observations over the following days and weeks, something became clear. This object wasn't bound to our sun. Its trajectory was hyperbolic, meaning it was moving fast enough to escape the solar system's gravity entirely. It had come from somewhere else, somewhere out in the depths of interstellar space. They designated it 3I Atlas. The 3I means it's the third confirmed interstellar object we've ever detected. The first was Oumuamua in 2017, that cigar-shaped mystery that passed through our solar system and left scientists arguing about what it was for years. The second was 2I Borisov in 2019, which looked more like a normal comet and gave everyone a sense of relief that maybe interstellar objects weren't all going to be as weird as Oumuamua. But then came 3I Atlas, and it made Oumuamua look normal by comparison. The first hint that something was off came from analyzing its orbit. When you calculate where an object came from and how long it's been traveling, you can make estimates about its age based on its trajectory and velocity. Scientists use sophisticated models, including something called the Tautahi-Oxford model, to trace 3I Atlas's path backward through the galaxy. What they found stopped them cold. This comet is old. Not just old like 1 million years old or even 100 million years old. We're talking between 7.5 and 14 billion years old. Let me put that in perspective for you. Our sun is 4.6 billion years old. Our entire solar system, everything you've ever seen in the night sky, all of it formed 4.6 billion years ago from a cloud of gas and dust left over from previous generations of stars. 3I Atlas might be older than our sun by billions of years. It could have formed when the universe itself was less than 4 billion years old, when the Milky Way galaxy was still young and most stars were first-generation stars burning bright and hot and short. This thing is a time capsule, a genuine artifact from an era of the universe that we can never visit, that we can only study through distant observations and theoretical models. It's been drifting through interstellar space for longer than our planet has existed, longer than our sun has burned. It witnessed the birth and death of countless stars. It traveled through regions of the galaxy we've never seen, through neighborhoods of space where radiation levels are thousands of times higher than what we experience here in our quiet corner. And now it's here, passing through our solar system, giving us a chance to study it. Except every single thing we've measured about this object makes no sense. Let's talk about the first major anomaly, the one that made scientists check their instruments multiple times because they thought something had to be wrong with their equipment. It's called polarization. When light bounces off particles, like dust grains in a comet's atmosphere, that light becomes polarized in specific ways. Think of it like how polarized sunglasses work. Light waves vibrate in all directions, but when light reflects off certain surfaces, those vibrations become aligned in particular orientations. By measuring how light from a comet is polarized, astronomers can learn about the size, shape, and composition of the dust particles surrounding it. Most comets show what's called positive polarization. The light vibrates in a pattern that tells us about relatively uniform dust particles made of familiar materials. Even 2I Borisov, the previous interstellar comet, showed polarization patterns similar to comets from our own solar system. 3I Atlas shows extreme negative polarization, the most extreme ever recorded. Using the Very Large Telescope in Chile, the Nordic Optical Telescope, and other facilities around the world, astronomers measured polarization levels reaching negative 2.7% at specific angles. The inversion angle, a key measurement in polarization studies, was 17 degrees. This combination has never been observed in any known asteroid or comet, not in our solar system, not in the previous interstellar objects, nowhere. To understand why this matters, you need to know that polarization tells us about what's actually on the surface of an object and in its surrounding cloud of dust and gas. Negative polarization this extreme suggests the presence of materials we don't typically see in comets. Water ice, yes, but also organic-rich compounds with unusual optical properties. Materials that might have been altered by billions of years of radiation exposure in ways we've never witnessed before. The only other objects in our solar system that show anything remotely similar are certain trans-Neptunian objects and a centaur named Pholus. These are icy bodies from the outer reaches beyond Neptune, and even they don't match 3I Atlas. The comet's polarization signature suggests it represents a completely different type of object than anything in our cosmic experience. But that's just the beginning, because when NASA pointed the James Webb Space Telescope at 3I Atlas in early August 2025, expecting to see a normal cometary composition, they found something that made the polarization mystery look simple. Comets are supposed to be dirty snowballs, chunks of ice and rock left over from the formation of planetary systems. When they get close to the sun, the ice sublimates, turning directly from solid to gas, creating the beautiful tails we can sometimes see from Earth. The ice is mostly water, with some carbon monoxide, carbon dioxide, and other volatiles mixed in. The ratio of these different ices tells us where and how a comet formed. Different regions of a protoplanetary disk have different temperatures, and different molecules freeze out at different distances from the central star. By measuring what's coming off a comet, we can essentially read its birth certificate. James Webb measured 3I Atlas's composition with incredible precision, and what it found was shocking. The ratio of carbon dioxide to water in this comet's atmosphere is 81:1. Let me say that again. For every 1 molecule of water, there are 81 molecules of carbon dioxide. That's 16 times higher than what we see in typical solar system comets at similar distances from the sun. Carbon dioxide makes up approximately 87% of everything this comet is releasing into space. This is not a water ice comet that happens to have some CO2. This is a carbon dioxide comet that happens to have a little bit of water. Nothing like this exists in our solar system, nothing even close. There are only 2 ways this could happen. Either this comet formed in a region of its parent star's protoplanetary disk that was completely different from anything in our solar system's history, with radically different temperatures and chemical abundances, or something happened to it during its billions of years in interstellar space that fundamentally altered its composition. Remember, this object has been exposed to cosmic radiation for potentially 10 billion years. Not the relatively gentle radiation of our solar neighborhood, but the harsh radiation near the galactic center and in the thick disk region where older stars orbit above and below the main galactic plane. That kind of exposure, sustained over geological timescales, could have literally transmuted elements on its surface, knocked hydrogen atoms preferentially loose from water molecules, created a radiation-hardened crust unlike anything we've ever studied. But we're not done, not even close, because the polarization mystery and the composition anomaly, as strange as they are, pale in comparison to what came next. Metal emission from comets isn't unusual. As a comet gets closer to the sun and heats up, not only does ice sublimate, but sometimes metals vaporize too. We've detected iron, nickel, sodium, and other metals in cometary atmospheres before. These metals come from dust grains that contain them, and under the right conditions, they get hot enough to release atoms into the gas around the comet. Whereas what's normal, when you detect nickel, you detect iron. Always, because nickel and iron are produced together in supernovae, incorporated together into dust grains, and locked together in the materials that build planets and comets. The ratio between them is predictable and consistent across the universe. It's one of the cosmic constants we rely on. Using the Very Large Telescope's UVS spectrograph, astronomers detected strong nickel emission lines coming from 3I Atlas. The comet was releasing about 45 grams of nickel per second. That's not unusual by itself. What's unusual is that there was no iron. Or if there was iron, it was so faint that it was barely detectable, and only when the comet was very close to the sun. Nickel without iron. That shouldn't exist. In nature, it doesn't exist. The comet's nickel production follows an extremely steep relationship with distance from the sun, scaling with the heliocentric distance to the power of -8.43. That's a remarkably steep dependency, suggesting whatever process is releasing nickel is extremely temperature sensitive and unusual. But here's where it gets truly bizarre. Spectroscopic analysis suggests the presence of nickel tetracarbonyl. That's a molecule with the formula NiCO4. One nickel atom bonded to 4 carbon monoxide molecules. Nickel tetracarbonyl has never been observed in nature, not in comets, not in asteroids, not in interstellar space. The only place humans have ever encountered it is in industrial nickel refining on Earth. It's a synthetic compound used to purify nickel through a process called the Mond process, where impure nickel is exposed to carbon monoxide gas at specific temperatures. And somehow, this interstellar comet is producing it naturally. The formation of nickel tetracarbonyl requires very specific conditions: low temperatures, high carbon monoxide concentrations, and some kind of surface chemistry that allows the bonding to occur. 3I Atlas's bizarre CO2-rich composition might provide exactly those conditions. The carbon dioxide could be breaking down through photochemistry to produce carbon monoxide right on the comet's surface, and that CO could be interacting with nickel-bearing minerals in ways we've never seen before. If this continues through the comet's closest approach to the sun, through what's called perihelion, it will represent the first clear case where an interstellar comet's metal emission is completely decoupled from normal refractory material release. It will mean there's a type of surface chemistry happening on this object that we don't understand. Chemistry that might only be possible after billions of years of cosmic ray bombardment fundamentally altered the molecular structure of the surface materials. Now let's talk about the water, because even though this comet is dominated by carbon dioxide, it is producing water, and the way it's producing water makes no sense either. NASA's Neil Gehrels Swift Observatory detected something unexpected. When 3I Atlas was still 2.9 astronomical units from the Sun, nearly 3 times farther from the Sun than Earth is, it was already losing water at a rate of approximately 40 kilograms per second. Imagine a fire hose at full blast. That's roughly how much water this comet was spraying into space, except it was doing it at a distance where the sun's heat is so weak that water ice shouldn't be sublimating at all. At that distance, temperatures are far too low for efficient sublimation. Water ice needs warmth to turn into vapor. That's why comets typically don't become active until they're much closer to the sun. But 3I Atlas was defying those expectations, releasing water at only a few locations where similar unusual activity has been detected. The Swift Observatory detected hydroxyl emission. Hydroxyl is what you get when ultraviolet light from the sun breaks apart water molecules. Each water molecule splits into a hydrogen atom and a hydroxyl radical. By measuring the hydroxyl glow in ultraviolet light, astronomers can calculate how much water the comet is releasing even when they can't see the water directly. The numbers they calculated were stunning. To produce that much water vapor at that distance, the comet would need an active surface area of at least 7.8 square kilometers. That means over 8% of its entire surface had to be actively venting material into space. Most solar system comets have active areas of just a few percent or less. This thing was outgassing like it was already close to the sun, except it was still nearly 3 times Earth's distance away. Near-infrared spectroscopy revealed the presence of icy grains in the comet's atmosphere. These particles are serving as an extended source of water vapor. Instead of water sublimating directly from the nucleus, the comet is spraying ice fragments into space, and those fragments then slowly sublimate as they travel away from the nucleus, creating a larger, more diffuse source of water than we normally see. Why is it doing this? Why is it so active so far from the sun? Nobody knows. But it fits with everything else about this object. Nothing about it behaves the way it should. And then there's the tail situation. Because 3I Atlas decided that wasn't enough weirdness, so it grew its tail in the wrong direction. In late July and August 2025, Hubble Space Telescope images revealed something that initially confused everyone who looked at them. The comet appeared to have a tail pointing toward the sun instead of away from it. Comet tails are supposed to point away from the sun. That's basic comet physics. Radiation pressure from sunlight and the solar wind push dust and gas away from a comet's nucleus, creating those beautiful sweeping tails that always point in the anti-solar direction. It's one of the most reliable things about comets. Except 3I Atlas had an anti-tail. A tail pointing toward the sun. This phenomenon isn't completely unknown. It's been observed before in a handful of other comets. What happens is that when you view a comet from certain angles, perspective effects can make it look like there's a tail pointing toward the sun. It's actually just the geometry of how we're viewing the dust stream, combined with the fact that larger, heavier dust particles don't get pushed away as quickly, so they lag behind in the comet's orbit and can appear to point sunward. But here's what made 3I Atlas unusual. The anti-tail wasn't just a minor feature, it was the dominant tail. For weeks, the most prominent feature of this comet was a tail pointing in the wrong direction. Observations from the W.M. Keck Observatory in Hawaii confirmed what was happening. The comet was releasing ice fragments primarily from its sun-facing hemisphere, and those fragments were large, around 100 micrometers in radius. They were ejected at speeds as slow as 5 meters per second. That's a slow walking pace. These particles were so large and moving so slowly that solar radiation pressure couldn't immediately push them backward. So they drifted forward in the comet's orbit for a while before gradually being swept back. Harvard astronomers Avi Loeb and Eric Ketto built a detailed physical model explaining the anti-tail. The exponential temperature dependence of ice sublimation creates a continuous increase in ice fragment production as the comet approaches the sun. But the residence time of those fragments in the outflow decreases sharply. The combination produces a peak in light scattering from water ice grains at a specific distance from the sun, around 3.4 astronomical units. Closer than that, the ice sublimates too quickly. Farther than that, there isn't enough being produced. As the comet continued approaching the sun through September, the anti-tail gradually evolved into a conventional tail.
temperature increases allowed smaller, faster-moving particles to escape, and those particles behaved normally, being swept backward by radiation pressure. But for a crucial few weeks, when the world was watching this interstellar visitor, it was growing its tail backward. Just another item on the list of things 3I Atlas does that it shouldn't. Now we need to talk about the mass problem, because this is where the statistics start to break down and scientists start using words like anomaly and unexpected in ways that mean something's deeply wrong with our understanding. By tracking 3I Atlas's position over time and comparing those positions to predictions based solely on gravity, astronomers can measure something called non-gravitational acceleration. That's the tiny push a comet gets from releasing gas and dust. As material jets off the surface, it pushes back on the comet, slightly altering its trajectory. Scientists analyzed over 4,000 positional measurements collected between May and September 2025. They combined this with data from James Webb about how much mass the comet was losing and how fast that material was moving. From all of this, they could calculate how massive the comet had to be. The answer? At least 33 billion tons, with a nucleus diameter larger than 5 kilometers. For comparison, Oumuamua was estimated to be somewhere around 100 to 1,000 meters across, maybe a few hundred million tons at most. 2I Borisov was probably a few hundred meters across, a few billion tons. 3I Atlas is roughly 1,000 to 100,000 times more massive than the previous interstellar visitors we've detected. Here's why that's a problem. In any natural population of objects, whether we're talking about asteroids, comets, or interstellar wanderers, small objects are exponentially more common than large ones. This is a fundamental principle that holds true across the universe. When something explodes or a planetary system ejects material, you get way more small pieces than large pieces. It's simple physics. Based on the population statistics we've built up from studying our own solar system and making theoretical predictions about interstellar space, we should have detected approximately 100,000 interstellar objects on the 100-meter scale before encountering something as massive as 3I Atlas. But we've only detected 2 other interstellar visitors, ever. Either 3I Atlas represents an incredibly unlikely statistical fluctuation, like winning the lottery 3 times in a row, or something is fundamentally wrong with how we understand the population of interstellar objects. Maybe there are way more large objects out there than our models predict. Maybe ejection mechanisms from planetary systems preferentially send out large objects in ways we don't understand. Maybe 3I Atlas is special in some way that made it more detectable than the thousands of smaller objects that might have passed through unnoticed. Or maybe it's something else entirely. The mass anomaly becomes even more significant when you consider the limited reservoir of heavy elements available for building such large objects. Stars and their planetary systems don't have infinite amounts of rock and ice. There are constraints on how many large comets can form in any given system. For 3I Atlas to be this massive and this old, wandering the galaxy for 10 billion years, it had to come from a system with specific characteristics we're only beginning to understand. But we're not done talking about how early this comet started showing activity, because scientists found something that extended the mystery even further back in time. NASA's Transiting Exoplanet Survey satellite, TESS, is designed to look for planets around other stars. It stares at patches of sky for weeks at a time, taking images every few minutes, looking for the tiny dips in brightness that happen when a planet crosses in front of its star. It's not designed to study comets in our solar system. But TESS happened to be looking at the right patch of sky at the right time. From May 7th to June 2nd, 55 days before 3I Atlas's official discovery, TESS was imaging the region where the comet was located. Scientists went back through the TESS data and stacked multiple exposures together to increase sensitivity. And there it was, a faint object gradually brightening as it moved across the field of view. 3I Atlas, already active, already producing a faint atmosphere of gas and dust when it was still 6.5 astronomical units from the Sun. The Zwicky Transient Facility in California had images going back even further. They tracked the comet out to 17 astronomical units, approximately 1 year before its official discovery. At that distance, way out in the cold darkness beyond Saturn's orbit, 3I Atlas was already producing dust at a rate of about 5 kilograms per second. Analysis of how the comet brightened as it approached the Sun revealed an extremely steep relationship. The brightness increased proportional to heliocentric distance to the power of -3.8. That's much steeper than 2I Borisov and more consistent with what we see in old comets from our own solar system that have made many passes around the Sun. But this is an interstellar object. It's never been near our Sun before. Why would it behave like a comet that's been repeatedly heated and altered by many solar approaches? By comparing data from TESS and Zwicky, researchers pinpointed when the comet began producing constant dust outflow, around 9 astronomical units from the Sun. That's just inside Saturn's orbit. And here's the key. That's exactly the distance where carbon dioxide ice starts to sublimate efficiently. This provides strong evidence that carbon dioxide, not water, is driving 3I Atlas's primary activity. As it crosses that threshold distance, its CO2-rich surface begins to sublimate, releasing gas and dust long before water ice would become active. This matches perfectly with the James Webb observations showing the extreme CO2 dominance. So now we have a complete picture of a comet that started becoming active far beyond the orbit of Saturn, driven by carbon dioxide sublimation, producing water ice fragments at distances where water shouldn't sublimate, releasing nickel without iron through some unknown chemical process, displaying unprecedented negative polarization, all while following an orbit that's about to bring it to its closest approach to the Sun. Which brings us to the trajectory, because where 3I Atlas came from and where it's going has raised some eyebrows among the people paying attention. The comet is following a hyperbolic orbit with an eccentricity of approximately 1.00016. That tiny number above 1 is what makes this orbit unbound. It's moving just slightly faster than escape velocity, meaning after it swings around the Sun, it will leave our solar system forever, heading back out into interstellar space. Its incoming velocity was around 44.58 kilometers per second. That's significantly faster than the previous interstellar visitors. And its orbital inclination is approximately 175 degrees, which places it in what's called a retrograde orbit. It's moving in the opposite direction from the planets. But here's what's interesting. Despite being in a retrograde orbit, it's only about 5 degrees away from the ecliptic plane. The ecliptic is the plane where all the planets orbit. Most objects arriving from random interstellar directions should be distributed evenly across the entire sky. Finding an interstellar object this close to the ecliptic plane is statistically unusual. The trajectory brought the comet close to several planets. It passed Mars on October 3rd and 4th at a distance of about 18 to 30 million miles. It's going to pass relatively near Jupiter's orbit on its way out. It came nowhere near Venus and Earth, but it crossed the inner solar system at a shallow angle.
On October 21st, 2025, the comet reached solar conjunction. That means it passed directly behind the Sun as viewed from Earth. We couldn't observe it for a period of time because the Sun's glare blocked our view. And on October 29th and 30th, it reached perihelion, its closest approach to the Sun at 1.36 astronomical units. That's about 203 million kilometers, just slightly farther from the Sun than Mars's orbit. At perihelion, the amount of solar energy hitting the comet's surface would be approximately 33 gigawatts. That's equivalent to about 1/3 of the total nuclear power generation capacity of the United States. All of that energy concentrated on a 5-kilometer wide comet nucleus.
This is when the outgassing reaches its maximum, when the surface temperatures peak, when whatever exotic surface chemistry is happening on this object goes into overdrive. And this is when spacecraft observations become critical. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter captured images of 3I Atlas during its Mars flyby. The comet appeared as a fuzzy bright dot from about 28 to 30 million kilometers away. Not much detail visible, but spectrometers aboard those spacecraft measured the light spectrum, revealing compositional information that confirmed what James Webb had found. NASA's MAVEN, Mars Reconnaissance Orbiter, and even the Curiosity and Perseverance rovers on Mars's surface attempted observations. The Emirates Mars mission gathered infrared spectroscopic data. But the best view is expected to come from ESA's JWST mission, the Jupiter Icy Moons Explorer. JWST is currently on its way to Jupiter, and its trajectory will give it an excellent vantage point for observing 3I Atlas in November 2025 using cameras, spectrometers, and particle sensors. There's been discussion about coordinating with NASA's Europa Clipper mission for ultraviolet spectroscopy observations. NASA's Juno spacecraft, currently orbiting Jupiter, might observe the comet in March 2026, though those plans remain uncertain. The International Asteroid Warning Network, a planetary defense coalition that normally focuses on potentially hazardous near-Earth asteroids, has launched an unprecedented observational campaign spanning from November 27, 2025 to January 27, 2026. This is the first time this organization has systematically targeted an interstellar object. Their goal is to monitor the comet's trajectory with extreme precision, analyze gas composition changes as it moves away from the Sun, and watch for any unexpected behavior. Anything that might indicate this object is more than just a comet. Because here's the thing nobody wants to say out loud, but everyone's thinking. Every single characteristic of 3I Atlas is anomalous. The age, the polarization, the composition, the nickel without iron, the water activity at the wrong distance, the backward tail, the mass that breaks statistical expectations, the early activity driven by CO2. One anomaly is interesting. 2 anomalies is a coincidence. But 8, 9, 10 major anomalies, each one independently challenging our understanding? At what point do we stop calling it a comet and start asking different questions? Which brings me to something that happened 48 years ago, something that might be the most unsettling connection of all. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected an extraordinarily powerful narrowband radio signal that lasted exactly 72 seconds. The signal was so strong, so clearly artificial in its characteristics, that astronomer Jerry Amon, when he saw it on the printout the next day, wrote one word in the margin: "Wow." The WOW signal has become the most famous unexplained detection in the history of SETI, the search for extraterrestrial intelligence. It came from a specific location in the sky, in the constellation Sagittarius, at coordinates of right ascension 19 hours 25 minutes and declination 27 degrees. The signal has never been detected again. Despite extensive follow-up searches over the decades, including dedicated observations of that same patch of sky, nothing like it has ever appeared again. It remains one of the great mysteries of radio astronomy. Harvard astronomer Avi Loeb recently did something interesting. He calculated where 3I Atlas would have been on August 15, 1977. Where was this interstellar comet 48 years ago when that signal was detected? The answer? Approximately 600 astronomical units away from our Sun. That's 600 times farther than Earth's distance from the Sun. Way out in the outer reaches of the solar system, in the region where the Sun's influence starts to fade and interstellar space begins. And more importantly, 3I Atlas was located at a position separated by only 4 degrees in right ascension and 8 degrees in declination from where the WOW signal originated. The total angular separation is about 9 degrees. Now you might think 9 degrees sounds like a lot, But from an astronomical perspective, considering we're talking about a signal's origin point 48 years ago and the current position of an object that's been moving through space all that time, 9 degrees is remarkably close.
Calm, curious, and informative, guiding listeners gently through surprising cosmic discoveries without hype. Now, read the following text. Loeb calculated the probability of this alignment being pure coincidence. The chances that 2 random sky directions would align this closely is approximately 0.6%, less than 1%. That's not proof of anything, but it's suggestive enough to make you wonder. If 3I Atlas was at that location and did somehow emit the wow signal, either intentionally or as some kind of byproduct of whatever it is, the transmitter would have required a power output of approximately 0.52 gigawatts. That's comparable to a typical nuclear reactor on Earth. For a comet to naturally produce a radio signal that powerful in such a narrow bandwidth at exactly the frequency the wow signal was detected would require mechanisms we don't understand. It's not impossible. Maybe there's some exotic plasma process or surface discharge phenomenon that could, under very specific conditions, produce such a signal. But it would require an artificial power source, or technology that uses principles we don't have access to. This is speculation, pure speculation, but it adds one more layer to a story that already has too many layers. An interstellar object that's 10 billion years old, covered in exotic surface chemistry, releasing metals through unknown processes, behaving in ways we've never seen, massive enough to break population statistics, was in approximately the right place at approximately the right time to have been associated with the most famous unexplained radio signal in history. The signal came from 600 astronomical units away. Now, 48 years later, that object has arrived at our doorstep. It's here. It's real. We're watching it. And every measurement we take makes it stranger. So what is 3I Atlas? What's the most likely explanation for everything we've observed? The conventional answer is that it's an ancient comet from a planetary system in the thick disk region of the Milky Way. It formed around 10 billion years ago in a protoplanetary disk with very different chemical abundances than our solar system. Maybe its parent star had a higher carbon-to-oxygen ratio, creating conditions where carbon dioxide was far more abundant than water ice. Maybe it formed near a CO2 ice line in a disk configuration we don't see in our neighborhood. After formation, some gravitational perturbation ejected it into interstellar space. Perhaps a close encounter with another star or a massive planet in its home system gave it just enough velocity to escape. And for 10 billion years, it drifted through the galaxy. During that time, cosmic radiation bombarded its surface relentlessly. High-energy particles from the galactic center, from supernova remnants, from cosmic ray sources we can barely imagine. That radiation knocked hydrogen atoms loose, preferentially removing lighter elements while heavier molecules remained. It created a radiation-hardened crust through processes we've only theorized about. It possibly induced low-level nuclear transmutations, slowly altering isotopic ratios over geological timescales. The extreme CO2 enrichment reflects its unusual origin. The lack of carbon monoxide, despite the abundance of CO2, suggests complex photochemical processing during its journey. The nickel without iron emission represents exotic surface chemistry activated by the comet's unique volatile composition, perhaps involving organometallic compounds that formed in the radiation-altered surface layers over billions of years. Its unusual metal emission patterns, particularly the possible nickel tetracarbonyl formation, hint at chemical processes that have never been documented in astronomical observations because they require conditions that only exist on an object like this: ancient, radiation-processed, CO2-rich.
The early activity driven by carbon dioxide sublimation, the water ice fragments released at unusual distances, the anti-tail phenomenon, all of these fit within known physics. They're just unusual combinations of normal processes. And the mass anomaly? Maybe we've just been lucky. Maybe 3I Atlas is rare, but not impossibly rare. Maybe in another decade or two, we'll detect more large interstellar objects and realize that our population models were wrong, that there are more massive wanderers out there than we thought. That's the conventional explanation, and it might be right. But there's another possibility, one that researchers won't state publicly without extraordinary evidence, one that violates no laws of physics but challenges our assumptions about what's possible. What if 3I Atlas isn't just a comet? What if it's a comet that's been modified, or a comet that's serving as camouflage for something else? A 10-billion-year-old object drifting through interstellar space could have encountered anything during its journey. It could have passed through regions of space we've never imagined. It could have been captured temporarily by other star systems, heated and altered, then ejected again. It could have accumulated materials from interstellar clouds with exotic compositions. Or, and this is pure speculation that scientists won't touch without evidence, it could have been deliberately sent. An ancient probe encased in or attached to a comet nucleus, using the comet's natural activity as both propulsion and camouflage. The WOW signal connection, while circumstantial, fits with a scenario where this object transmitted a beacon 48 years ago when it was far enough out to avoid detection, announcing its approach. The mass anomaly, the unusual trajectory that brought it so close to multiple planets, the timing of perihelion coinciding with solar conjunction when it was hidden from Earth-based observation for crucial days, these could all be coincidences, or they could indicate something more. I'm not saying this is an alien probe. I'm saying that every measurement we've taken has shown us something we've never seen before. And when you're dealing with something that's 10 billion years old, that's traveled through regions of the galaxy we can't observe, that displays chemistry we don't understand, you have to at least acknowledge the possibility that our explanations might be incomplete.
The evidence is real. The anomalies are documented. The observations come from the most sophisticated instruments humanity has ever built. James Webb, Hubble, the Very Large Telescope. These are not amateur observations or blurry photographs. This is solid scientific data showing us an object that doesn't fit our models. And in November and December 2025, as the International Asteroid Warning Network conducts its systematic observation campaign, we're going to learn even more. Every spectrum, every image, every measurement will either confirm that 3I Atlas is an extraordinarily unusual but natural comet, or it will deepen the mystery even further. Scientists are watching for specific things. They're monitoring whether the nickel emission without iron continues as the comet moves away from the sun. They're tracking any changes in the CO2 to water ratio. They're looking for variations in activity that might indicate venting from specific locations rather than uniform sublimation. They're measuring the trajectory with extreme precision to see if there are any non-gravitational accelerations that can't be explained by normal outgassing. And yes, some researchers are quietly watching for any signals, any electromagnetic emissions in radio frequencies, microwave frequencies, anything that might indicate this object is more than it appears. The WOW signal connection, as tenuous as it is, has put this on the radar of SETI researchers who normally wouldn't pay attention to a comet. Because here's what makes this different from Oumuamua and all the speculation that surrounded it. With Oumuamua, we had one major anomaly, the non-gravitational acceleration that couldn't be explained by normal cometary activity. That was enough to spark debate. Some scientists proposed exotic explanations. Others argued for natural mechanisms we just didn't understand well. But with 3I Atlas, we don't have one anomaly. We have nearly a dozen.
each one independently unusual, each one pushing the boundaries of what we've seen before. And when you stack them all together, you get an object that feels less like an outlier and more like something fundamentally different. The age alone makes it special. This is one of the oldest objects we've ever had a chance to study up close. If it really is 10 billion years old, it formed when the universe was only about 30% of its current age. The first generation of planetary systems, the first wave of planet formation across the galaxy. Everything it's made of, every molecule on its surface, dates back to an era we can only glimpse through distant observations of early galaxies. It's a messenger from deep time, a sample of materials and conditions from a cosmic epoch we'll never be able to visit. Even if it's just a comet, even if every anomaly has a natural explanation, 3I Atlas represents an unprecedented opportunity to study the evolution of materials over billions of years in interstellar space. The surface chemistry alone is worth years of research. If cosmic rays really did alter its composition over 10 billion years, creating exotic compounds and unusual isotopic ratios, then this object is a laboratory experiment we could never reproduce. We can't bombard something with high-energy cosmic rays for 10 billion years. We can't create the conditions of the thick disk region of the galaxy in our labs. But nature did it for us, and now it's passing through our neighborhood where we can study it. The nickel tetracarbonyl, if that's really what we're detecting, opens up entirely new questions about chemistry in extreme environments. How does that molecule form naturally? What other organometallic compounds might exist on this surface? What happens to mineral structures after billions of years of radiation damage? Can cosmic ray bombardment really induce nuclear transmutations on geological timescales, gradually shifting isotopic compositions in measurable ways? These are questions we've never been able to ask before because we've never had access to an object like this. And if, and this is still a big if there turns out to be any evidence of artificial modification or technology associated with this object, that would be the most significant discovery in human history. It would mean we're not alone. It would mean intelligence exists or existed elsewhere in the galaxy. And it would mean that civilization, whatever created or modified this object, did so billions of years ago. Think about that timeline for a moment. If 3I Atlas is associated with technology, that technology would be ancient beyond comprehension. Our species has only existed for a few 100,000 years. Civilization as we know it is only about 10,000 years old. We've had radio technology for barely a century. Something that's 10 billion years old would predate everything we know by a factor of more than 1,000. It would come from a time when the galaxy was young, when most stars were still first-generation population 2 stars, when the heavy elements we take for granted were far less abundant. What could a civilization that old have achieved? What could they have built? And if they sent probes or markers through the galaxy, objects that could survive for billions of years while drifting through interstellar space, how many of them might be out there? And it reminds us that we're living in an incredible time. The first generation of humans who can detect interstellar visitors. The first civilization on Earth capable of studying objects from other star systems. The first to ask these questions with instruments sophisticated enough to actually find answers. Whatever 3I Atlas turns out to be, we're watching history unfold. We're part of the story now. The story of an ancient wanderer that crossed the galaxy and, for a brief moment in cosmic time, passed close enough to our world for us to see it, study it, and wonder about its origin. The answers are coming. Every day brings new observations. Every week brings new analysis. The scientific papers are being written. The debates are happening in conference rooms and observatories around the world. And slowly, piece by piece, we're building a picture of what this object really is. Until then, we watch, we measure, we question.
And we remember that the universe is under no obligation to make sense to us. It simply is what it is. And sometimes what it is turns out to be far stranger than anything we expected. Subscribe for more updates as this story develops, because trust me, this is just the beginning. These are the questions that astronomers are thinking about, but not always saying out loud. Because without evidence, speculation about alien technology is just science fiction. But the evidence we have so far keeps refusing to fit into comfortable boxes. Every interstellar object we've detected has been strange in its own way. Oumuamua with its cigar shape and unexplained acceleration. 2I Borisov with its high carbon monoxide content and unusual polarization. Now 3I Atlas with its extreme age, bizarre composition, exotic metal chemistry, and statistical improbabilities. 3 objects, 3 completely different signatures. What does that tell us about the diversity of planetary systems across the galaxy? What does it tell us about the processes that eject objects into interstellar space? And what does it tell us about how common these visitors actually are? Based on the detection rate so far, astronomers estimate that there could be thousands of interstellar objects passing through the inner solar system at any given time. Most of them are too small or too dark to detect with our current surveys. We're only seeing the tip of the iceberg. The ones that happen to get bright enough, close enough, and lucky enough to pass through our field of view at the right time. Projects like the Vera Rubin Observatory, which is set to begin operation soon, will dramatically increase our detection rate. That telescope will survey the entire visible sky every few nights, going much deeper and seeing much fainter objects than current surveys. Within a few years of operation, we might be detecting dozens or hundreds of interstellar objects per year. And if every one of them is as weird as the first 3, our understanding of planetary systems and the galaxy is going to undergo a revolution. Because right now, our models are based almost entirely on our own solar system. We assume that what happened here is typical. That the composition of comets from our outer solar system represents the standard case. That the processes that formed our planets are the same processes that form planets everywhere. But every interstellar visitor is teaching us that we might be wrong. That our solar system might actually be unusual. That the diversity of planetary systems is far greater than we imagined. That carbon-rich systems, oxygen-rich systems, systems with different formation timescales and different radiation environments all produce different populations of comets and asteroids with different compositions and characteristics. 3I Atlas might represent a population of ancient, radiation-processed, CO2-rich comets that are common in certain regions of the galaxy but don't exist in our solar system because we formed under different conditions. Or it might be a 1 in a billion rarity. We don't know yet. We need more data, more objects, more observations. But what we do know is that the universe is more diverse, more strange, and more interesting than we thought. And objects like 3I Atlas are the key to understanding that diversity. As this comet continues its journey outward, leaving our solar system behind and heading back into the dark between the stars, it will gradually fade from view. The sunlight will diminish, the surface will cool, the outgassing will slow and eventually stop. Within a year or two, it will be too faint and too far away for even our best telescopes to track. And then it will be gone, returning to the interstellar night from which it came, continuing a journey that began before our sun existed and will continue long after our sun dies. Somewhere out there, 10 billion years from now, if it survives that long, 3I Atlas might pass through another star system. Beings that don't exist yet, in a future we can't imagine, might detect a faint comet entering their space. They might point their instruments at it, whatever form those instruments take.
They might measure its composition, study its surface, analyze its trajectory. And they might wonder, as we're wondering now, where it came from, what it's seen, what secrets it carries. Because that's what 3I Atlas really is. Not just a comet, not just an interstellar visitor, but a messenger, a time capsule, a sample of the galaxy's deep history delivered to our doorstep by chance or fate or cosmic coincidence. The evidence is real, the anomalies are documented, the observations are solid. Whether 3I Atlas is exactly what it appears to be, an extraordinarily unusual natural comet, or whether there's something more to the story, something we're only beginning to glimpse, the answer matters. Because it tells us about our place in the universe. It tells us about the diversity of worlds and objects beyond our experience. It tells us that the cosmos is full of surprises, that billions of years of history are encoded in objects we're only now learning to detect and study.